get started. So it's my pleasure to introduce Ron Clowes, our speaker this month. We got a lot of history for this talk, and I think it'll be pretty exciting. So Ron is born in Calgary, received his BSc in 64, his MSc in 66, and his PhD in 69 from the U of A. In 1970, he joined the Department of Geophysics and Astronomy at UBC, and he retired in 2007, but is still a professor emeritus. In 1987, he was appointed director of Lithoprobe, which he held until the project concluded in 2005. His personal research has been centered on multi-channel seismic reflection, seismic refraction, wide-angle reflection, and other geophysical studies of the lithosphere on land and at sea. For nearly 30 years, his research was associated with the Lithoprobe, and as director, he was instrumental in both its success as a project and its international acclaim. Through his research and Lithoprobe, he has received numerous awards, including the Order of Canada, the Fellow of the Royal Society of Canada, and the Logan Medal of GAC, and honorary membership of the CSCG, plus I'm sure many, many others. So with that, I'd like to welcome Ron and learn about Lithoprobe.
Well, it's a pleasure to be here, and I thought that I suggested to Ross when I couldn't attend the symposium last November that maybe I could give a talk like this because it has relevance to the mineral industry and exploration as opposed to the lithospheric studies that I was most often working in. So you can read the title, I don't have to say it. This isn't moving. It just takes a while, I see, okay. It's a little slow. Okay, so Lithoprobe, as Ross said, was a 26-year project, ran from, or 30-year project, ran from 84 to 2005. And really it was a national project involving many universities, government, industry. And the basic theme was to investigate the 3D structure and the evolution of the Canadian landmass, and we did work offshore as well. And it had a lot of contributions to Canadian earth science, but two that I just wanted to emphasize was that it fostered an unprecedented degree of cooperation among earth scientists from all sectors, university, government, and industry, which unfortunately I think has gone downhill since then in terms of the cooperation. It also spawned a new and healthy atmosphere of scientific collaboration with the geologists, geophysicists, and geochemists all working together. And that hadn't happened much prior to Lithoprobe. So the purpose of this talk is to emphasize much of things I just mentioned. Geophysicists and geologists must work together. Geophysical and geological data should be combined. You probably all know that, to get the best possible interpretation. And in terms of geophysics, in terms of detail, the seismic reflection is the principal geophysical method to combine with geology for underground and deeper penetration. And Lithoprobe has demonstrated these points through the multidisciplinary program that we ran over all those years. And we did it for primarily lithospheric studies. That was the real basis of Lithoprobe to start with. And then as we got on and became a very successful project, we got involved with industry and using seismic and other techniques in exploration examples. And that's what I'm going to feature today. So there's 5 exploration examples. The Guichon Creek batholith in Highland Valley area of British Columbia, the Matagami deposits in Abitibi Greenstone Belt in Quebec, the nickel deposits in Sudbury, and uranium exploration in northwest Saskatchewan, and looking at a diamondiferous kimberlite dyke in the Northwest Territories. So it covers a lot of types of mineralization and locations across Canada. Oh, there we go. So I'm not going to go into it either, try to explain the abbreviations here, but because it's so slow in terms of reacting here. I hope I'm not doing something. Thank you. So those are the 10 transects of lithoprobe outlined by the polygons. And the 5 examples I'm talking about are in southern BC, Quebec, Ontario, Northwest Saskatchewan, and the Northwest Territories. So it's important when you're combining geophysics and geology, as you probably well know, to look at the petrophysics side of things, as well as having as much subsurface information as possible. So this is just an example of P-wave velocity versus density, showing that minerals such as pyrite, pyrrhotite, and etc. are way off on the away from the Drake curve, which is the gray band going through here, and all different types of rocks. So what this means is that they may be suitable impedances and reflection coefficients associated with the mineralization compared to the host rocks, let's say. And another thing that you want to get involved in is drill hole data. These are log-derived density, fracture velocity, and then the subsequent impedance, the product of velocity and density. And you can see that massive sulfides have a distinctive signature in terms of this drill hole lithology, and therefore could represent a good target for seismic reflection. So the first study doesn't like me. It's gonna take a little longer though. So the first study is in south central BC in the Highland Valley area, and you have the porphyry copper deposits associated with the Guichon Creek batholith, which is outlined by the ellipse there. So this is a detailed geology map from Kimberlite, who no longer exists, I guess. Well, not in the way they used to anyway. And there's another high-res aeromagnetic map of the same region. You can see the batholith corresponds to quite low magnetic values. The outline on here in dashed lines is a 3D inversion using the Oldenburg inversion technique on aeromagnetic data. So I'll show a little bit of results from that. The seismic line is the red line along here, reflection line, and it goes right across the region that these are deposits. 3 purple marks there are the deposits. And so what we did was we took this regional lithoprobe, original line, reprocessed it, and then worked with the data provided by Kimberlite and other information, geology or gravity and magnetics, to come up with a cross-section of the batholith. So this is the there we go. So this is reprocessed reflection lines. This is a regular lithoprobe reflection line, which meant it was did not have parameters designed for high resolution studies, but we were able to reprocess this. A postdoc, Shelley Roy, and I worked on this. And you can see, I think, even at the distance you're looking at, the reflections in there. And so this is a reprocess. This is a coherence filtered version of that, in which the interpretation has put on it. And you can see that basically the batholith in which the copper deposits are found is like a mushroom shape with a funnel and then expands out. And you can actually identify the limbs on the east and the west limbs from the reflection data. You could not see that on the original processing. So this is the regional Bouguer gravity anomaly map. And this is our line along here. when we recorded seismic reflection data in any of our profiles, we also recorded detailed gravity information along the same profiles. So we've got the regional gravity that is typical from the GSC, and then we've got detailed work along that particular line as well. And you can see that the batholith outlined by the ellipse is pretty much associated with low density material. So here's the high resolution aeromagnetic data that was provided by Caminco. This is the original map, and here in the dashed line show the phases of the batholith. Then we use the Oldenburg and Lee, Oldenburg and Lee inversion. And this is the calculated map that comes from the inversion following that. And you can see there's a series of low susceptibility anomalies A, B, and C. A is an actual known deposit. These have not been explored further. And these are just slices from the three-dimensional inversion. And at Z equals 2,000 meters, you can see A, B, and C on the slice at that point. This is just the projection of those anomalies to the surface on this map here. And then putting all that together, we managed to draw a cross section with the geological map there, and then the cross section showing the various phases. And these are the ore deposits showing on the surface as well as extending to depth. So we were able to put together a more detailed geological model of the Guichon Creek batholith from putting all these studies together. The second example is the Abitibi Greenstone Belt in the Matagami area, which is volcanogenic massive sulfides. There's a number of mines that were already known when we did our work, Eeldu and Matagami Lake. Bell Allard, which is going to be the focus of what I'm talking about, was discovered in 1992. And we ran a high resolution seismic line 93A along a road that was right almost beside the deposit. And this made a good test case because the mine had not been developed or anything. So it was just a deposit identified by drilling. And then we ran our seismic. So it's undisturbed, so to speak, as opposed to trying to do anything over the mines themselves that already existed. I'm not going to go into the background geology of all of these, or you'll be here for longer than you probably want to be. So this is just something to give you an idea. Okay, it might be sensitive to my thumb touching. So this is an orthographic projection from a lot of mineral mining studies within the mines, or in this case, the Matagami Lake deposit, which was on that previous map. And so it has a lot of folds in it, and then it's truncated by I think it's a diorite dike or something down on this side here. But that's what the top of the keatite surface, and that's associated with the massive sulfide deposits. This is from the Eeldu deposit, the other one that I showed at the yellow stars. And this is a geological cross-section with no vertical exaggeration, showing the massive sulfide in here in lenses, probably feeder tubes for the massive sulfide up in here. And the key tuffite is just this little bit down in here. But that's a key to the, no pun intended, that's the key to understanding some of the massive sulfide deposits, because they all seem to be associated with the just above the key tuffite, which is the here's an underground exposure of it, the key tuffite with the andesite below. We did, in this case, there's a significant amount of borehole geology undertaken, and the density, P-wave velocity, impedance. In this case, is not a large impedance contrast. This is the andesite right in this part in here, and the key tuffite is just below it in there. And there are various other lithologies that are shown here. This is a synthetic seismogram, which doesn't show up anything particular that you would see in terms of the mineral deposit if you had one. So this is the seismic reflection line along there. The main reflections are from the Gabbro sills, like this here. This is the top of the Bell River complex, which is the lower part of the complex in that region. The Bell Allard is in this region in here. The key tuffite, it's not showing up as a reflection, but knowing from the rhyolite and the reflectivity there, knowing and having drill hole information in this area, of course, we're able to identify where it should be. Now, an expanded version for the rectangle is supposed to come up when I do it properly. There we go. So this is an expand. So this is an expanded version of the previous section. And just take a look at, we're only looking at 400 milliseconds depth here. So this is quite high resolution in this area. And the Bell Allard deposit is this one down in here. There's no reflection from the Bell Allard deposit, but you can see, you can identify the various geology, and the advantage of what the seismic gave in this case, because you couldn't identify a deposit, was that it gives the structural control between their drill holes, so they could follow the lithology is much better that way. The third example is the nickel deposits in the Sudbury area. This is an outline of the Sudbury basin and the whole Sudbury igneous complex. What we're interested in are the norite layers and the Gabbro layers. That's where the nickel deposits are found. And what I'll focus on is a reflection line that'll tie this one. We'll move it over this way and tie these in one reflection cross section. Excuse me. We'll look at a north-south line across the same area. And then this was the first attempt at a 3D seismic, high-resolution seismic survey over a known deposit, again, before it had been mined. So it was a test whether you could identify a deposit with 3D seismic. So just to remind you about impact craters, this is the Sudbury schematic cross-section. And the parts we're interested in is that part up in here, where you have the Gabbro and the norite layers up in there, and the rest of it is just, and this is the result prior to any tectonic deformation, because the Sudbury impact structure has been deformed by subsequent tectonism. And just to give you for the geologists in the group, give you an idea, there's a norite melt, granitic melt. And these are the shatter cones. And this is the shatter cones, as an aside, they're often used to identify impact structures around the world. We did a significant amount of logging in this region, or the company did. We were working with what's now Vail and somebody else. I think it was Falconbridge and Inco at the time. And you can see that there's actually some, in terms of the P wave velocity and the resistivity, the magnetic susceptibility, the norite actually tends to have a bit of a signature in some of these characteristics. And so it's possible that this combined with the geophysical data helps us understand and follow things better. So this is a geological cross-section along that blue line from south to north. And just dipping that is the result of the subsequent deformation. The arrows here are all drill holes. We've got a fair bit of shallow drill hole information to tie to. And I think you can see that why the interpretation was put it way it was. This is the granophyre and the gabbronorite in those two colors there. And they extend down. And you can see the same thing over here where there's not quite the mining primarily has been the north range, but there's also some in the south as well. So this is a gravity profile and the interpreted density model associated with the gravity. So the usual 2.5D, you can see the calculated as the light line, the observed as the dark and heavy line. And based partly on the seismic results combined with the gravity data, the interpretation is probably better and more constrained than you would expect from just a regular gravity interpretation, because gravity is not very unique, as we all know. So we did the same thing for the magnetic profile, pretty much. So this is essentially the same model as you saw previously, and the various susceptibilities were associated with these rocks based on some of the logging data and also laboratory studies. And you can see that these are drill holes in here. And the altered norite, so this is on the south range down this region, and this is the north region down in here. And so I think the magnetic and the gravity with the seismic combined to give a pretty distinctive cross section for the Sudbury structure. I mentioned the 3D, which was on the southwest side of the Sudbury structure in the original map. And this is where we carried out a high resolution 3D survey. So this is the surface plan for the survey with a number of lines going this way and the shot lines are that way. And it was then processed using standard 3D software. This is a vertical slice from northeast to southwest, northeast to southwest. And what is interesting is that the sublayer, and particularly the base of the sublayer, there's fairly prominent reflection that you can identify in there. The red lines are drill hole, or these lines are drill holes. The red is with the Sudbury igneous complex. The sublayer is the black part, and into the footwall complex is the blue. Most of you won't be able to see that. It's blue down here. So the interpretation is controlled a lot by the fact that you have drill hole information, but at the same time, you can see that there is some more coherent reflectivity in this region than on either side of that. And then we're able to put together a perspective view of the footwall contacts. That's this one here, which is the green, what you're seeing here in green. There's the surface plan in this perspective view. And the known mineralization in here that was discovered, but known prior to this study, but had not been mined yet. This is the ore deposit. And the ore deposit was not imaged. So it's very difficult to image an ore deposit. But what was found on this slice of the seismic, 3D seismic, at about 1,800 meters depth is this diffraction pattern. So basically what's happening is the seismic waves are coming down, hitting the ore deposit and providing a diffraction pattern because it's an inhomogeneity that causes diffractions. And we're picking up that diffraction pattern. And this technique has been used subsequently in a number of places. And in particular, after we did this, there was an attempt by one of the mining companies in New Brunswick, and they actually found a new deposit using 3D seismic of this type. When they drilled the new deposit that they found, it wasn't economically viable, but the deposit itself was found. Can't say much about the content of mineralization from the seismic, that's for sure. Okay. There we go. So the next one that I wanted to talk about are these uranium deposits in Athabasca Basin, Northwest Saskatchewan. We did this, and again, with all of these studies were done in collaboration with industry as well as the groups within the Geological Survey of Canada. So this is the Athabasca Basin in Northwest Saskatchewan. And there are a number of uranium mines. In fact, it's one of the world's largest uranium sources of uranium, even today, I believe. But we carried out a high resolution line up in here where we'd previously done some regional work. And then in this region, we did another high res line and a pseudo 3D along the MacArthur River deposit. So what we're going to look at is, first of all, a section of this line here, and then we'll come back to work around MacArthur River. Well, this is the details of the region we're looking at. So the main features we want to look at are the Manitou Falls Formation, which exists in this sort of band of colors across here. Yes, 2D high-res line is this one here. And the MacArthur River region is over in here. It's the uranium deposits are often associated with this major fault, the P2 fault, which is exposed at the surface in this region here. So that's a target for the work that was being done. And the S2D was done partly along an existing line. And then we did some detailed work over in this region here, which will come up later. All the deposits are, there's one there, there's one there, there's one there. There's a number of different, another one over here. So there's a number of deposits that have been mined and we're producing uranium. The MacArthur River was a more recent one. So this doesn't look like much of a seismic section. This is the S2D. That's this little short one across here. And the interpretation on it. Now, the next slide will show detail, but you can see there's quite strong reflectivity up in this region. This is the end of the Athabasca Basin, and this reflectivity here just drops to an end, and this is a basement reflector outside of the edge of the Athabasca Basin, as defined, of course, by the geology. And you look, we're only looking at 0 to 2000 milliseconds, and the lower part is, I'm not sure how all these interpretations came on, to be honest. It's not my interpretation. Final is held from 2010. But the important part for what we're talking about here is the next slide shows this, an expanded version in here. And I think you'll see very clearly that the high resolution seismic really does provide information. This is the unconformity along which most of the uranium deposits are found along this unconformity. And there tend to be various types, sometimes sort of large bodies, sometimes they're lenses, and a very type. The black lines on here are interpreted faults that have offset the unconformity and extend up into the sandstone unit that overlies the material below. So within the MacArthur River region, this is a magnetic map of it. We did a regional line, and within that line, we also did some high resolution ones, line 14 and line 12, which we'll show you line 12 because it lies close to the deposit. And then we did a pseudo 3D, which is basically combining information from the 2D lines plus not as good of 3D as was done at Sudbury, but it was putting together various shots from here recorded here and from shots in here recorded there, etc. So you can get a what they call pseudo 3D. Here's the enlarged portion of the regional line. This is about a 12-kilometer section across here. The unconformity is up here. This is showing the P2 fault zone, which is this reactivated thrust. It's a reverse fault. And this is a basement reflector that has no relevance to the deposit. It's something that showed up on a number of lines and which was a totally different story. So we'll look at a more detailed version from line 12. And here's the unconformity along here. The sandstone fill for the basin is up in this region here. The P2 fault zone is these dipping reflectors in this region underlying the unconformity. These are pure bodies in this region, and these are drill hole information. This is drill hole information here. We also had borehole, some login information from one of the boreholes. So there was reasonably good constraints on being able to interpret what was going on in the seismic. Again, if you just took the seismic by itself without all the subsurface geological information, I think you'd have a pretty hard time coming up with a appropriate interpretation. So putting all of these results together in the 3D and the pseudo 3D, this is a display of that. And the colors are showing you the depth to the unconformity. So the lower the blues, the reds and yellows are the highest. And there's actually a offset from the upper part to the lower part of about 100 meters along this P2 fault, which is this fault showing here in gray along there. There's actually a bit of a flower structure that shows up in the seismic data in this region in here. A flower structure is essentially when you interpret a structure that looks like has a number of what should I say, parts to it, and then leads down to into a sort of a single feature on the seismic data. And they're often found in the sediments when they're looking for petroleum. So the pods are the uranium pods in this particular display are shown by the dark black ones, which are tied to the offset between the unconformity being down and up and along the P2 fault. And the scale here is 500 meters, so you can get a sense. So the deposits themselves are not very large. And once again, it's mainly getting control on where you might find the faults and the unconformity, offsets, etc., in terms of trying to locate where you might want to explore for the uranium deposits. Now, before I go on, I should say that this turned out to be, for the uranium companies, very, very valuable. They have continued doing it at their total expense, going to companies in Calgary to get the seismic data. And they've been using that as far as I know, at least until a few years ago. And they continue to do it because what they find is using the seismic with all their own information they have from geology and drill holes and being able to identify the unconformity and where faults are on that unconformity has helped them considerably in identifying new deposits. And of course, this is rather important if we're going to go further with nuclear energy in the future, to have deposits and of uranium for us, and particularly for Canada. We want to go on with this and keep to Canadian things. So my final example is this diamondiferous kimberlite dyke in the Northwest Territories. Now, this was a totally unique seismic study. Nothing had been done like this before. We got involved with De Beers and Diamond X. This was a postdoc working with me, or a research associate and myself were working on this one. And this is the Slave Province. With little diamonds are more than 150 kimberlite discoveries that were made mainly in the 90s. There was only a few mines, of course. Guyavik is one of them. I forget what the other one was. Snap Lake is this one here. So this is the Snap Lake discovery. I think if I push that, something comes forward. Yeah. That's the Snap Lake. Kimberlite is this one in here. And this is what we're focusing on. And what was going on here is they had identified subcrop the diamondiferous kimberlite, and then instead of being the usual deposit type for diamonds, this one was a dyke, and so it had lateral extent, but it was very thin and aerially extensive in the subsurface. And the point of the study then was, could we map this dyke by doing high resolution seismic? And this is what we were involved in for back in the early 2000s. So why was this unique? Well, a dyke is extremely thin target, extends to considerable depths. So the question then is, are there sufficient amplitudes at high frequencies to identify this? There had been no comparable exploration scale studies of this type ever undertaken that we knew of at the time. And there was no geophysical well log information available. So what are the impedance contrasts going to be between the host rock and the kimberlite and the dikes? And we had no information about how much attenuation the rocks themselves were going to give to the seismic information. So a couple of questions were, is the reflection method an effective and cost-efficient exploration tool? And can these studies provide useful information for drilling, for drill guidance, and for perhaps future mine planning? So just a generalized cross-section of the Snap Lake Dyke. You've got a granite host. You got this very thin intrusive sheet that averaged about 2.8 meters in thickness. The depths went, it's a degree, about 17-degree dip. Depths went from subcrop. There was an access, forget the word you use now to get access into the subsurface. And so with subcrop to at least over 1,000 meters depth. So that's just a schematic cross section. This is too, but this is the kimberlite dyke. So you've got subcrop that way, goes down to at least 1,300 meters. There's some drill core information, and this is a sample taken from one of the, or a photograph taken from one of the drill cores in that region there. Undulations on the variable thickness, 1 to 5 meters for the dyke itself, averaging the 2.8 that I mentioned before. It had variable dip. See that showing up on here. And it had very complex zones with feathering and offsets and stuff like that. And the contact zone with the granitic coast was very narrow. It's only 1 to 10 centimeters. So that's not going to show up at all, but it means it's a very prominent contrast between the properties of the dyke and the granitic host. So because this was a unique experiment, we had to do we did a feasibility study ahead of doing any seismic. We had to determine what parameters might work. How would we carry out the study? As I said, there's no comparable experiment to go by. So we took a number of rock samples from the region, and the group at the University of Alberta did P wave velocity versus depth or pressure measurements. These are the host rocks and various other ones. Here's the pegmatite dikes. These are mafic dikes along here. And the kimberlite comes way down here. So low velocity relative to the host rock and other rocks in the area. And the different colors and symbols just have to do with various measurements that were made at Alberta in terms of going up in pressure, down in pressure, and different samples. This is sort of a composite of a lot of the work that they did. And if you look at the 25 megapascal, which is just in this region here, about 25 meters depth or something like that, the pegmatite had values like this, but the kimberlite was at 4.3 kilometers per second, 2.49 grams per cc, which is very low compared with any of these other numbers up here. And therefore you had a large impedance contrast, impedance being the product of velocity and density. So we did a lot of seismic modeling, knowing properties of the dike and some of its variabilities. So we did a substantial amount of in-house laboratory studies, not laboratory, computer modeling. And this is just one example. So we did a lot of seismic response modeling of this kimberlite dike, but with various configurations, thicknesses, feathering, etc. So this is an example, which is just finite difference modeling of the response of a feathered dike. So here's the model of the dike with 4.3 kilometers per second embedded in 5.6 kilometers. This is 1 meter thick, this is 5 meters thick, and there's feathering in here. This is to contrast it with just a straight slab within the host rock. And the three panels shown here are for 400 hertz, 200 hertz, and 75 hertz. And this is 200 hertz just for the slab. And you can see that 75 hertz does not identify anything to do with what is happening with the dike. 200 hertz, you can start to see a little bit of it. You're getting a reflection from the top and the bottom. You don't see that over in here. But at 400 hertz, you're starting to get a little better definition, but this does not look exactly like that. So there are issues with trying to use high resolution seismic in terms of the dike itself. So the conclusions from the computer modeling were the following. We need high frequencies, 200 to 400 hertz. The amplitudes returned below 500 meters depth are going to be very low. So that was going to require some fancy processing. Turns out that because you get a larger reflection coefficient if you go to larger offsets sometimes, because you're getting total reflection instead of just using the vertical incidence impedance contrast, which we often look at. So longer offsets were advantageous in terms of that. The dike thickness is not expected to be defined because the dike thickness is just too thin for the frequencies we were looking at, and with the attenuation that naturally exists within the Earth. There we go. And again, as I indicated from the figure before, the fine scale dike structure is not going to be imaged with these exploration scale acquisition layout. But the company still felt that we should go ahead and carry out the survey and see what resulted. Oh yeah, and then I've already mentioned the fact that you have to maximize your signal to noise by your careful computer processing that you're going to do with the data. So the Snap Lake, it's called Snap Lake Dike because this is the adit where the underground goes under from in here. And the dike itself extends laterally and aerially below Snap Lake, and in this region. We ran two lines, one that was primarily explosives along here, and another using high resolution vibra size or high frequency vibra size, because we could not do explosives in the lake itself because of the fish situation and that. So this is the where the line was constrained. These are the coordinates, northerns and easterns, etc. And one less the squares there. Maybe I'm not pointing this sufficiently, but here we go. So the circles on here are drill holes. The size of the circle indicates the intersected depth of the dike from 4 meters to 1 meter. The colors indicate the depth. So you can see it's dipping this way, dipping in this way here. This is pretty much all of the same depth in this region. And then it's a dike that's going this way to the northeast. So this is, we had a fair bit of drill control to work with in terms of what we could, how we could interpret the seismic line. As I said, not pointing. Here we go. So the explosive line was 5.8 kilometers long, and it was down dip. This is the best we could run it. The sources were 1/4 kilogram pentabyte charges. There was 480 shots along the line. The shots were drilled 1 to 3 meters into bedrock, and depending on where we were along the line, we have 4, 8, 12, 16, or 24 meter spacing of the shots. So the higher resolution, or the closest shot spacings were in the shallower part of the dike, and the further ones were out in this region, out in here, the deeper part of the dike. That was to minimize the cost. Of course, drilling and explosives are expensive. Okay, there we go. So the receivers, we used 0.5 millisecond sampling rate. The geophones are 28 hertz. We had 816 single phones, 816 channels, in other words. Asymmetric split spread. It was a 2 meter spacing between the geophones from 0 to 1.44 kilometers, and a 4 meter spacing between the geophones from 1.44 to the 5.86, which is the length of the line. And the longest offsets were about 3.2 kilometers. Couldn't record the entire line at the same time. A couple of shots. So this is a drilling rig, shot hole drilling. The track rig, we sometimes had to use towed or heliported drilling rigs because of the environmental issues that we were dealing with. It turns out the time we were up there in 2000 had a very early spring, and the snow, and it started to thaw prior to us completing the survey, so we couldn't use the track rig everywhere. And and then the geophone deployments, they plowed a line along the region here. You can see the geophones in this case, probably pretty close to 2 or 4 meters, and a little bit closer up of some of the individual geophones, all of which were each geophone is telemetered to the central recording station. No, I'm wrong. I think they record on here, and then that all goes to the central recording station. I can't remember for sure. It was processed by a commercial company. We did not do the processing. And there's what a charge looked like. 1/4 kilogram charge. Used a backpack firing block, and what you need to know about this handsome fellow sitting there, that's me. That's the boss of the project sitting there doing my usual hard job. of reading a book. What is going on?
Did most of the holes vent like that?
Did they?
Most of the holes, did they vent like that?
I don't really know. I wasn't along all the entire survey, but that's fairly typical, I think, of what happened, because they're only 1 to 3 meter deep. And so there's very little tamping on them, so they probably did vent. And the reason for the 1/4 kilogram was to get the higher frequencies. Okay. Oh, I didn't even know these computers, I better not do that. There.
That's
Thank you. Oh, no, maybe that's it. Yeah. What happened when we got to the screws? Bring your hands down. That's what I wanted. Yeah, thank you. Oh, yeah, that one there. Oh, that's okay. It's a shot gather. It's filtered from 200 to 400 hertz. And this is over a fair distance here. The offset 500 years. Here's where the shot was here. So this is ground roll refractions, which are always the first arrivals. The dyke reflection is actually coming in this region here, and you can follow it down in here for something you can actually follow it there. And
But you had a couple hundred receivers out at one time?
there was 800 receivers. I don't know how many. I think they were all active at one time. We just moved them along. Something like that. It's so the technology that the seismic industry can use now is quite amazing from what we used to do. I mean, I used to do seismic results where we put a seismometer every 15 kilometers. That was for the search studies. That's an aside. So now let's take a look at this thing. It's coming up on here.
Oh, it's just need to.
Oh, it's the one before that, which is the button I want.
Just up and down. Well, that will do it.
No.
Give it a chance. Yeah, it needs to update. Yeah, it's good. Good.
No, that's not the one I
No,
want.
we're good now. Yeah.
Oh, there we go. So what I wanted to show, this is the reason I wanted to show this. If you just take a little enlargement of this major reflection profile, this is what it looks like. We're only looking at from 150 to 190 milliseconds of travel time. And you can see the dyke comes in very clearly as a strong reflection when you enlarge things. So you can actually follow it quite well, which was very reassuring to us, having spent a fair bit of effort trying to decide what we should be doing to run the survey. So this is the whole survey along line 1. The dyke is imaged all the way from up in this region here, from near subtrough, all the way down. You can see it changes dip, has different characteristics. That one's got that on.
Yeah, it's
It'll take a while, that'll.
No fuck. We would say.
Oh, there we go. So we can float all the way down to probably below 1,200 to 1,300 meters. We can call the dyke on this MHF with all the migrated stack and the processing that we put into it. This works properly. It worked on my computer, but. So this is just showing you the line, of course, what you saw before. But here we go. So put an interpretation of the top of the dyke. all along here based on the reflection results. And okay, is that really what it is? Well, those are the drill holes within 50 meters of the line. These 5 drill holes here within 50 meters. And you can tell they intersect and they terminate in the dike. So the termination dike, the drill holes totally confirm that that is the dike that we are seeing. And then there are a lot more drill holes. And every one of them defined where we could see the reflections or a series of reflections, etc. And this is just a repeat. What a kimberlite core looked like. This is 1.63 meters from the core, just a photo. So the interesting thing here was we were able to image this dike right down to 1,300 meters, even though it was very thin and a very poor seismic target. As I understand, Snap Lake was subsequently mined, of course, and now it's mined out. It's no longer an active diamond mine. In fact, I'm not sure none of the ones in the Northwest Territories are active diamond mines anymore. Dyke, or what's he begins with a
Caddy.
the Caddy, thank you. The Caddy died, Dyke, and Snap Lake. None of them are. They're all mined out now. I think the main diamond mine in Canada at the moment is one in northwestern Ontario. I can't remember its name. Anyway, so that turned out to be a very successful project working with De Beers and Diamond X, which is a small diamond exploration company, which I'm not sure exists anymore. This was back in 2000. Oh, and then I did want to just show you an enlargement of the section in here, so you can see this. What the reflection looks like. This is the drill hole information. The numbers on here range from basically most of these are 3 meters, but here's one at less than a meter drill hole intersected. You can see that it varies in depth where the reflection is. So it was very clear that we were able to image the dike very, very clearly and tie it in with the geology from our geological results from the drill holes. So that's it. So what I want to say is the 5 lithoprobe studies that I just presented demonstrate the value, I think, of the combined interpretation of geological, geophysical, especially seismic reflection data, by bringing those together. You really couldn't have done the seismic interpretations with the geology. And in many cases, the value to the minerals industry of the high resolution seismic reflection technique for exploration and mine development, particularly in regions where you already have substantial drill hole and other infrastructure information. The various techniques of high resolution seismic have been used subsequently since we did our studies in a number of mining regions. And as I said, in the terms of uranium, it's, I believe, still, I don't know if it's continuing to this day, but certainly was continuing until a few years ago when I was talking with my colleague, Dolly Heinel, who was primarily in charge of all of that work. So those are just some examples of how Lithoprobe, which was a academic project, if you want to put it that way, looking at the lithospheric structure of all of Canada, how it came together, and in working on that particular aspect, we also were able to tie in with industry and do a lot of work that turned out to be quite valuable with industry. So, and in fact, from a funding viewpoint, we ended up having to do that as time went on because our funding agencies required that we get more ties with industry from that when we started out. So there's a few incentives beyond just the fact that industry was interested, but it worked out extremely well. And I must say that I had a wonderful career as Lithoprobe director. Thank you very much.
Wonderful, thank you so much for that talk, the history of where it came and the successes they've had. Is there any questions in the room for Ron?
And have to speak up too. I wear hearing aids and, you know, I'm aged.
Just curious how the vibrosize worked on over the lake. I guess that was frozen.
I was expecting a question like that. The vibrosize did not work well.
Was it on the ice surface or
Yeah,
down
it
the
was
bottom?
on, no, it was on the ice surface, yeah. Had to do it in the winter time when the ice was frozen, when there was sufficient ice that you could stand the weight of the vibrator and everything. But there was just too many multiples from between the surface and the water. I mean, obviously we tried to get rid of them, but we did see a little bit of it. Diamond X actually carried out a subsequent survey over another area, which I didn't show here. It's in it. We wrote this postdoc and I wrote a paper about it. And in that we've got the example from Diamond X. They just provided, we didn't do anything. They just provide other than quality control, but we just took the results that they had got from the company that did the processing. And they did get some results from looking at the dike in another region. But as far as the over the water, no, it just didn't work. We also had a few explosives from land recording on the geophones on the lake. We did get some response that way, but it wasn't of the quality that you saw here for the land only line. So it would work with land into geophones on the ice, but not with vibrosize on the ice with geophones on the ice.
Ross, I gotta say that I wish we had gotten hold of you because this talk fit in so beautifully.
I agree.
The symposium is an opening talk and it really would have fit beautifully.
Thank you. I was planning on attending the symposium, but I ended up having to go attend the celebration of life for a colleague who was a close colleague from Lithoprobe, and this was on Salt Spring Island. It's a University of Calgary professor, Edward Cook, who had passed away. He had retired and moved to Salt Spring from Calgary. He was active. He's active. I mean, some of you'll know Jim Mortensen, former geologist in our department. He and Fred were working actively in southeast BC in terms of looking for critical mineral deposits and things like that. At the time that he just had a stroke and passed away. So I had to, in fact, Ross and I were in touch. I had to defer, say that I planned on attending. I joined the society if I could use to attend this. And I was unable to attend for that reason. But yeah, I would like to have been here because it was something that I mean, obviously I'm not going to be doing anything myself, but I was still interested in what's going on. And that symposium looked to be very interesting that way with the speakers. Although I think I only recognize one or two of them in terms of their names. They're all much younger than I am. Yes.
What's the status of the Lithoprobe data?
All the Lithoprobe reflection data are available at no charge from the Geological Survey of Canada. There's a website. I would say about every 1 or 2 times a month, I end up getting an email saying, I'd like to see some of these data. I've looked on your Lithoprobe website, which has been extant for quite a long time. It doesn't really have a lot of information other than the basics from 30 or so years ago. And so I put them on. I've got a website that I got the information from my colleague, Don White, former student from UBC that worked with me. He's really in charge of that sort of thing at the GSC at the moment. And he can give the person a website, then you can just go on and you've got to know what transect you're interested in, what lines are available, and you can get the seismic data and the data information that goes with it in order to process it if you want. The magnetotelluric data are all filed as well, the same way at the GSC. All the magnetotelluric data recorded throughout the project, which was in most transects. We did some additional magnetotelluric data. You were involved somewhere, Dennis.
No.
Oh, okay. You were involved in something in Ontario, weren't you?
Yes.
Yeah.
No variation.
Yeah. Okay. And the seismic refraction data, most of it should be available partly, not that many people want to use it because it's only for large scale things. But it's, I think the main refraction data will be there. The mistake I think we made in Lithoprobe is we did not put into the archive our processed or interpreted refraction results after, because you have to go through a huge process to get the structural interpretation or velocity interpretation from the seismic refraction data. And that is only available through the publications, as far as I know. The data, refraction data, should also be available through the IRIS website in Seattle from the USGS, because we partnered with USGS in many of our surveys in terms of them providing instruments, because we didn't have enough of our own in Canada. So but it was important to archive as much data as possible. There's also a couple of, we tried to get each transect. Well, you have to realize we started in '84. This is before the digital revolution, so to speak. So, but subsequently, when the digital world came to the science, the earth sciences, we tried to get each transect to prepare a CD of results, and some were able to, and some weren't. And some those CDs still exist, but they don't really contain the data. They contain a lot of information about the transect reports, which is another thing that we never did digitize, which probably should have been, because I've had requests for papers out of our transect reports that are no longer available except in print form. So you have to have it, and I don't have my print copies anymore. But others, some people do. Anything else? Went beyond the question. I'm done. Go ahead.
Yeah, so usually when we think about kimberlites, there are always these dyke coming up. So what was special, either geologically or whatever happened to actually make a dyke like that? Where is that?
Yeah, I was gonna ask the same thing. Is that, dyke is cross-cutting
That's correct.
stratigraphy. The
Not
geometry of that,
necessarily.
I call it more of a
I think
still.
in this case, the dyke is tied in with the lithological change from one type to another. So somehow the dyke exploited a weak path that was going, in this case, dipping in one particular direction.
Was
That's
it a
my
more appropriate name, geologic name for that, a sill? Rather
No.
than a dyke?
No, a sill is more or less what you described at the beginning. That basement reflection that was on one section that I said had no relevance to this talk, that was a sill. And another fellow and I actually analyzed the data from that, and it is a sill. And we found that in Alberta. The other thing is, going back to the question about archiving, the Alberta basement data, which was a substantial amount of data, recorded partly with industry money. They provided a couple of million, I think, for some of the seismic acquisition costs. Those data are still being requested as well by people that are interested in the exploration side in the sediments of Alberta and Saskatchewan, as opposed to the mining industry. So there's still quite I wouldn't say there's not a lot of interest, but I think we made a very wise decision in archiving all of the data so that it could be looked at and reprocessed where necessary, especially now that there's a lot more availability in terms of sophisticated processing techniques that weren't available when we were doing our work.
So is snap plate kind of an anomaly then?
Yes, somewhat. There are other kimberlite dikes, I believe, but I'm not sure about that. But yes, it was quite an anomaly. But the thing was, it had been discovered originally, if I remember right, by just, a prospector going around picking up samples of, well, there's a diamond here. There's nothing that should be necessarily.
G10 garnets is how it was found.
Okay. Anyway, so I can't, I could look it up in the paper. There's more information in the paper, which I've got a copy of on my computer, but I don't remember all the details we didn't go into a lot about the dike itself in terms of how it was emplaced or anything.
I assume that Trill is the Trillabelle deposit?
I suppose so. I mean, it was a.
That's, it's
it
got
was
the right
something
depth
fine.
location.
Yeah, that's probably why it's called
Yeah.
drill 3D.
The diffraction pattern,
Hmm.
did you model it?
It has been modeled, yes. Yeah.
Is it possible to work?
Bernd Milkerite at the University of Toronto has done some modeling on it.
So it might be possible to trace back, knowing the density and velocity of a massive sulfide, putting that into the model, it should be possible perhaps to figure out the size of the massive sulfide from the
That I
diffraction
don't know.
pattern.
I've not heard of that being done. What has happened, of course, is when they picked up these diffraction patterns, then you've been able to focus the diffraction pattern back to the source, so you can find out where the deposit itself is. But I don't know of anything that's been done exactly what you were suggesting. I've not heard of the size of a deposit being determined. As I said, it was successfully used in New Brunswick, finding a new deposit. I know that, but it was, when it was drilled, it was not economically viable. Yes, Rob.
We have Richard Smith online. Richard, you can go.
Yeah, sorry.
Yeah,
Richards.
thanks very much for the talk, Ron. That was great.
Oh, you mean we've got,
I've never
Here's
seen a
the
lot of that snap lake data. Can you tell me where it's published?
where what is published, the paper?
The snap lake one, yeah.
In Geophysics, the journal Geophysics.
All right.
Yeah.
You one of the authors?
Yes. Hammer and Clowes. Hammer, Hammer, and myself.
Okay.
It may have been Ramachandran. I can't remember if he was on that paper or not, but there was Hammer and Clowes were the first two authors. And the paper on which this talk is based was published in Geoscience Canada in 2017 as a Logan medalist special paper.
Thank
Any
you.
other? That took me by surprise. I have to say.
I've got a question that's completely off topic, but where does Canada stand in the total amount of, lithoprobe scale, the large scale surveys compared to other countries like China, Australia, US, Europe?
Well, Canada's pretty well gone, nothing happening in Canada. Really, since Lithoprobe, there's been very little done. I mean, that was the peak of Canadian lithoprobe or lithospheric studies. There's work going on, of course, with earthquake studies in terms of mantle features and looking at other things. The Chinese have a huge program that they call Sinoprobe, it's called Sinoprobe because it was modeled after Lithoprobe. And I was a scientific advisor to Sinoprobe. So I've been over there a few times, looking at their data and that. But it's a huge project in China. As far as I know, it is still ongoing. And it's gone above just like a project like this one, like Lithoprobe was. It's a ministry level endeavor. So they're using it for mining exploration, petroleum exploration, trying to understand earthquake risks. There's lots of earthquakes in some of the areas there as well. So they run a lot of high resolution surveys and things like that. I haven't kept up with it that closely. The last time I was involved with them over in Beijing was in 2018.
So it would be larger than Canadian.
Oh, very large. Oh, yeah, it also involves a drilling component.
Right.
So there was the Canadian drilling program, of course, that went on for a short while.
Where does the Australian lithoprobe?
The Australian, they had a group within the Australian Geological Survey that was all done within government in Australia. It was not done through the academic side. And I don't know, we used to have every 2 years a international seismic meeting held all over the world. And that's where all the different groups from around the world would be presenting their stuff. But again, there's not a lot of that being done. And I don't even know if those meetings are still being held. Someone else may know the answer to that question. I don't. So I think there's been such a shift from lithospheric and even understanding the upper 10 kilometers, been a big shift from that in the 80s, 90s to environmental studies in the 2000s, of course. And when you look at NSERC funding and everything, you see that NSERC funding is highly directed towards the environmental side as opposed to the solid earth side. And so solid earth geophysics, solid earth geology, etc., is probably not at the same napier that it was in the 80s and 90s. And we got going in Lithoprobe in the 80s because we had fallen so far behind what was happening in the States. And we made the argument that we should be getting into that. And the big change we made from the United States was we did it multidisciplinary. First, they did a seismic program called COCOR, and then they anticipated having geologists just flood into their work, which did not happen. I mean, they got some very fine results, don't get me wrong, but it wasn't an integrated multidisciplinary study like we did. And that's what the Chinese are doing, is an integrated multidisciplinary study with the follow-up of drilling, which we didn't have the advantage of. So they've drilled down to 12 kilometers, I think, or something like that. Looking at seismic features.
The seismic conferences are still going on.
Oh, are they?
Seismic, size IX, is that what it is?
No, it used to be, I don't remember what let me just try to think. This is from the one that was in somewhere in Norway or something, I think. But anyway, I don't remember. They're called deep seismic profiling of the continent. It's called deep seismic profiling of the continents. Was what the conferences were called. And they started out in the US around 1980, early 80s. And the first one in Canada was Alan Green of the Geological Survey, and I organized it at Banff in 1990. And they've been going every 2 years at least until into the teens of the 2000s. But as I said, I don't know if you may know more about it than I do.
Yeah, I think this one might be reflection seismic.
Well, they've expanded towards the end, they expanded beyond reflection to include refraction and then the high resolution earthquake inversion processes they were using to get 3D velocity structures. So that was all included in the latter ones of the conferences that I attended. But I haven't been to one of those for, I don't know, 15 years at least, probably.
Well, fantastic with that. Thank you, Ron.
Thank you for your attendance.
And if a group